Hi everyone. Today you're on in Canvas as always. This one is a review from Unit 4 as well, but it will be pertinent to our lesson today also. So go ahead and do it. If you want to see an example of where this came from, you can look in Unit 4. In the beginning of the unit, it would be close to the front. Independent events, I believe we did about taco tongue and evil eyebrow. So you can check that lesson out. Okay. Pause, complete this, then unpause to see the answers. All right, so one thing I thought that made this a little bit easier was right here where it says, suppose to randomly select one of the survey, define C as 4 or more children and S as 1976. And so I just went ahead and labeled those in the chart. That made doing P of C given S a lot easier. So C given S means that we only look at this column, the S column. So our denominator is 100. And then of those 100, 40 had more than 4 children. C given not S would be everywhere else. So there were 200 of those. And 26 had 4 or more children, the 13 and the 13 added together. Then independent events, if you remember, we have P of A should equal P of A given B and P of A given not B. So if any of those three don't equal each other, then they're not independent. And what that means is just that B has no effect on A. So A will occur the same frequency of times or proportion of times whether or not B happens. So in this case, looking at whether someone has was born in, whether we're looking at 1976 or the 2 other years, the proportion of women who have 4 or more children should still be the same across those 3 years if they're independent. But it appears that in 1976, there were more or a higher proportion of people with 4 or more children. Okay, so let's get out the activity about M&Ms again, but this time we're doing does the type of M&M matter? So we're going to work through this front page together, and then we are going to do the second page. You're going to do that on your own. So we'll do the front page together. First, just go ahead and add up these rows so that we have the totals. We'll need them for our activity. And so we don't have M&Ms to give you today. I'm so sorry about that. But we are going to use some that were already created, so we'll have the same numbers to work with. And that is where we'll start. So first, how many samples do we have, and what populations are them? So we have Miss Bailey and Miss Pendleton are wondering about the different types. So we have 2 types of M&Ms, and that means that we had here 2 samples. Plain and peanut M&Ms. And then of those 2 samples, we're looking at one variable, the color distribution. And so not 2 variables, just one. Now for this hypothesis test, we haven't learned this yet, so we're going to do it together. But remember, the null is always that there's no difference in whatever we're looking at. So in this case, we have 2 groups, plain and peanut M&Ms, and we're looking at the color. So I'm going to write there is no difference in the distribution of colors for plain and peanut M&Ms. I'm not claiming to know the distribution of colors for either one. With last class, we actually discovered that the distribution that was reported by Google is not the one that actually matches because there was way more greens than we expected. So I'm not claiming to know what the distribution is. I'm just saying that they're the same for both plain and peanut. But our alternative is just going to be the opposite of that. There is a difference in the distribution of colors for plain and peanut M&Ms. All right, number 4, we're going to use a chi-square test to determine if there's a difference. So we need to get the expected values. I did make a mistake on this worksheet. It says observed again when I copied the table over. So make sure you cross that out and put expected. And then what we have is an empty table. So if the null is true, remember, we always assume the null is true to do our expected. The null says there's no difference in the distribution of colors for plain and peanut M&Ms. So what I do know is that there were 242 red M&Ms out of 1,850 red M&Ms. Now that, and then there were 850 plain and 1,000 peanut. So what I know is that right now, 242 out of 1,850 gets me 0.1308. So I'm just going to write this off to the side. That means that right now, regardless of the type, 13.08% of M&Ms are red. And so if there's no difference in the distribution, that means that 13.08% of the plain M&Ms should be red and 13.08% of the peanut M&Ms should be red. So what I'm going to do now is multiply that number by 850, and that gets me what I expect to have for the plain M&Ms. And I'm just going to round to 1 decimal inside the table. I expect out of the 150 M&Ms for 13.08% of them to be red, which is 111.2 M&Ms. And then for the peanut, same thing. I'm going to do 0.1308 times 1,000, and I'll get 130.8. That should still add to the 242 because it's still all 242 M&Ms are broken down. I also could have done, of the 242 M&Ms, I expect 850 out of 1,850 to be plain, and then 1,000 out of 1,850 to be peanut. So now I want you to use that same method to find the rest. I'll help you with a couple. So let's just fill in the totals again. 332, 248, 364, 240, 424, and then that does total to 1,850. So remember, what I want you to do is find the proportion of each color, regardless of the type, first, and then multiply that proportion by the total for each type. So for the next one, I'll do 332 out of 1,850. I got 0.179, and then I'm going to times that by 850, and I get 152.5. And I'll do 0.179 times 1,000, and I get 179.5. And again, there's a lot of ways to do this, but I'm just going to stick to the same way. So you can pause here and finish, and we will fill this in. There. So pause to finish it up. And I'll go ahead and write the rest in. So those are the expected counts. Now, before we get too far, I want to let's just go ahead and debrief a few things in red on this page because I think it's going to be really helpful for the next page. So first, in a table, this is a two-way table, just like on our warm-up. And so I want to kind of make sure you guys see that the totals are not part of the table. And so this has 1, 2, 3, 4, 5, 6 rows and 2 columns. So we call it a 6 by 2, 6 rows, 2 columns. So the totals do not count. We have 2 or more samples. So when we have 2 plus samples, that is what makes this a chi-square with one variable. That's going to make this called a chi-squared test of homogeneity. And that word means we're testing whether the distribution of one variable is the same or different in multiple groups. So in this case, we have 2 groups, 1 variable of color, and our null is no difference. And our alternative is there is a difference. So you might see same for the null and difference for the alternative. And then for the expected counts, what we did was we really took the idea of that independence from the warm-up, and if there is no difference in the distribution, then the proportions should be the same all the way across. So basically, I should get, P of plain, or what we did actually was P of red should equal P of red given plain, and P of red given peanut. That's what we really did. So the formula that we ended up using is your row total multiplied by the column total divided by the table total. So if you go back and try those again, if we do 242, so let's do an example. That would be 242 times row total times, so if I do this one, times 850 over 1850. That is actually the exact math we did. It was just we did it one step at a time. So we did 242 over 18 and then times 850. And so same math, but now you can use this formula to get the answers instead of your doing that logically. And one more time, I'm going to exclude the totals. They're not part of the actual table. So go ahead and make sure you know that these are our expected counts. So when you guys do your chi-squared test on the next page, your L1 can have all of the observed counts. Your L2 can have all of the expected. Just make sure you go in the same order. So I recommend that you just, start here and then go across. Don't do the totals. And then again, in your L2, you start here and then go across. So that you should have 12 entries total, and they should match up so that when you do your chi-squared test statistic, you get it to work. Last thing I need to tell you before you do that is you'll need to know the degrees of freedom for a chi-squared test with the two-way table. And remember in the last unit, it was just categories -1, but now we have 2 sets of categories. Now we have 6 colors and 2 types of peanuts. So what you do is you take one away from each, and then you multiply them together. So officially, the formula is going to be number of rows minus 1 times the number of columns minus 1. So in this case, that's 6 minus 1 times 2 minus 1 equals 5. So one way to visualize that is you just take a row and a column away. Let's see if I can. So it's like, okay, let's take that row away. Oops. Take this row away and this column away, and then you count 1, 2, 3, 4, 5 cells left. So that's one way I do it too. Okay, so go ahead and fill in the past template on the next page for this problem. I already gave you a couple of the things like the procedure name right here and the formula for degrees of freedom, and then some tips on how to enter this in your calculator to get all the rest. So give it a try, unpause when you are ready, and I'll go over the answers. Oh, right. So this is always the null and alternative for a chi-square test of homogeneity. No difference and a difference. Or remember, like I said, they are the same. Or more. We could have looked at pretzel M&Ms and caramel M&Ms and had 4 different types. So it depends. And then here, the 2 or more distributions. Those are different ways to say it. For the thing here, I'm going to remind you that we always show the first, second, and the last. Like we talked about before. Now, just make sure they match up in your list. It doesn't. Everyone could do. Someone could have gone vertically and then gotten first and second to be different, but it doesn't matter as long as you show your work there with the dot 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 in the middle. And then we got our p-value, our chi-squared. Picture is the same, and our stuff like that. Make sure you include the DF. So if you haven't written it down on this screen, make sure you do. And then for the expected counts, you want to include a labeled table of expected counts. So we have that right here. It's labeled as expected right here. So, and then you fill it in. You don't have to do the totals, but you do need to include that. And I just include it in the A section since I'm checking the expected counts condition there anyway. And because this was 2 samples, I had, my 2 columns like I like to do when there's more than 1 sample involved. So, and then of course our last S has not changed. And number 6, explain how this is different. So what I want to show you is a little bit about how to tell the different types that we do. And so far we've learned 2 of the types, and those 2 types are based on a one-way table where we have 1 sample, 1 variable, and we did that last class. That is where we use L1 and L2, and we get, what do we do? It's called a chi-square GOF test. Goodness of fit test. This other kind is when we have a two-way table, like today. And we actually have 2 kinds of tests that come out of a two-way table. In a two-way table, we could have 2 or more samples and 1 variable. And that is when we do the chi-squared test of homogeneity. But there is another kind called chi-square test of independence. That's when we have one sample with two variables. And this one is called a chi-squared test of independence. So we're actually using that exact same language from the warm-up to determine if variables are independent from each other. So that's the main difference between them. Now I want to show you how to do this in the calculator. So if you guys would, go ahead and take out your calculator. It's going to be a little bit tricky in here at first. So you got to follow all the way along. Let's see, get the right thing out. Okay. So I said L1 and L2 are for goodness of fit tests, and you may have used L1 and L2 today because we hadn't learned anything else yet. But I do want to show you that we have stat test has some options for us. So if you go to stat and then go to test, there is something called just a regular old chi-square test. You'll see the GOF test there as well. But we're focusing on the chi-squared test. So well, actually, let's click on GOF. There you have L1, L2. You put the observed in L1, you put the expected in L2, and you write your own DF. We're not doing a GOF test right now, though. We're going to do stat test, just a regular old chi-squared test. This works for any two-way table problem. And so I'm going to click that. What you see here are these brackets with the capital letters A and B, and these are actually matrices. So what we have to do in order to use the chi-square test feature in the calculator is we have to make a matrix of the observed values. And it's so cool, I'll show you. It will make them expected for us. So what I want you to do is go to the home screen, and we're going to hit second x to the -1, that's the matrix button, and then go over to edit. And so for this problem, we have, like I said, a 6 by 2 matrix. So I'm going to type in a 6, hit enter, type in a 2, hit enter. And so it should be the two-way table. Do not include the totals. And then from there, what we're going to do is fill in the observed values. The observed go into matrix A. And so we have 119. Oops, nothing's typing. 119, 123, 168. You can just hit enter and it goes across. 164, 93, 155, 182, 182, 115, 125, 173, and 251. And then I really recommend that you check this over because it's very easy to make a typo, and doing it this way, you'll never know that all your answers are wrong if you don't check. There. So then from there, you're going to hit second quit. And then, I'm telling you, this is so easy. You go stat, tests, chi-squared test. Whenever there's a two-way table, that's the one you'll pick, not GOF, chi-squared test. And then we put the observed in A, but it will fill in the expected for us after we hit calculate. So hit calculate, and I got this p-value, or the chi-squared of 18.338 and the p-value 0.0026, just like I got on my actual paper. And it tells you the DF as well, so you don't have to fill that in. But what you do have to do is continue to show work with the first, second, and last, and then you do have to draw the picture, and you do have to write a labeled version of your expected values. So to get those, you go to second matrix, and then notice how there's a matrix B now with the same dimensions as matrix A. I like to go to edit and then look at matrix B from there because it puts it all on the same screen. And then there's our expected counts. We did not enter those in. It did it for us. So that's a really nice feature of the calculator that you can use. Just make sure that your paper still has the first, the second, and the last shown and a picture. I also want to remind you about the draw feature if you're not sure how to draw your picture. In the test feature, you go stat, test, chi-squared test. And I could have clicked draw instead of calculate. We do that sometimes on the other tests. Oh, there's my box plot still in there. You can ignore that. And so if you're wondering what does the chi-square look like, if you have trouble drawing it just based on like the DF and all that, then you can draw it here. And notice how it's not shaded at all because 18 is off the screen. That's fine. So that's what it looks like, skewed to the right. Okay, so I am going to let you copy down all of this. We've already pretty much talked about everything on here. But again, there is one new type of test when we have one sample with two variables. That's called the chi-squared test for independence, and it just has a different HO and HA. So I do want to actually only difference is how you write HOHA between these two. And so with the homogeneity, you have two samples, and we're just comparing one distribution across the two groups or more. And with the test for independence, we're seeing is there an association between the two variables for the one population. So it's kind of an important difference, but that's the only thing different about them. So pause here to copy it down and then try to check your understanding. And I'll go over some tips and tricks on the next page. All right, so this is the biggest part of this unit is how to determine different types of distribution or different types of tests. So we have the first one. The hardest part about these is determining which type is which, and then once you do that, then you can use the same methods for each one, mostly. So for this number one, we have shopping at secondhand stores becoming more popular, and so they have a study of customers' attitude at separate random samples. And so when there's more than one sample, that makes it homogeneity. And then what we want to see is the distribution of gender the same for each store or different? So our null will be that they're the same, and our alternative would be that they're different. And again, I want to show you in the calculator one more time how easy it is to get the chi-squared, the test statistic, the p-value, and the expected counts. So I'm going to do that really quickly. So remember, you go to second matrix, and then you can just write over the other one. This one would be a 2 by 2 because we don't include the totals. So I'm going to change it to 2 by 2, and then I just fill in 38, 68, 203, and 150. And so then I hit stat tests, chi-squared test. I don't have to touch anything. It will write over it for me. A, B, calculate, great. And I get 15.334 and 9.01 times 10 to the negative 5. And it gives me the DF of 1 for me. But, you could still calculate it yourself using the formula. Remember not to include I don't like that. How that looks. Don't include the totals for your matrix or for your DF or for your expected counts. Now, speaking of expected counts, we do like for on a past problem on a 4-step process that you find those and label them. So go over to edit, and now matrix B should be filled in. And so what you do is you just recreate the table and label it expected. We're going to put those numbers in there. You can just round to 1 decimal place. I'm writing them down now, so hopefully you are too if you haven't already. And so I just put them like that, and then you want to label this expected. So the next one, it said that on this one, we have a random sample of adults, and then they also labeled them by their higher education. So you cannot tell from the table, but this was one sample, and then they asked them about their opinion on astrology, and then sorted them by also their degree held. But they didn't separate the group into associates, bachelor's, and master's and ask 3 separate groups. The question, they asked one question and then separated them by their education. And so this was called a chi-square test of independence because it's only one sample. And so then the variable, there's 2 variables, and that's here and here. So on this one, we have our degrees of freedom, test statistic, p-value. Again, in my calculator, I could just go over to the matrix. I can edit it, just rewrite over. This is a 2 by 3 this time. And so not a 2, there we go, 3. So I just type in 169, 256, 114, 65, 65, and 18. And then, oops, that says 19. So make sure you check your work there. And then we just do stat tests, chi-squared test, and that's where we get everything from. Oh, I always do too many pushes. Okay. Calculate. 10.58, 0.0050, and then we do second matrix, edit, look at matrix B for R expected. And so again, I want you to make sure you just copy that down onto your paper. So you just make a table, label it expected, and then rewrite associates, bachelors, masters, and not versus vary. And you just copy these numbers down like that. So I'm just going to let you guys do that. And this last one, number 3, is a chi-squared GOF test. And the reason why is because we had one-way table. So anytime it's a one-way table, you don't have to choose between the types. It's just a chi-squared GOF, no questions about it. But remember, you put your observed in L1, and then for your expected, take your sample size, 200, and multiply it by each of the probabilities. And so that would be red, black, green. And so in this one, we have to use L1, L2, and L3. So actually, I'll show you how another faster way to do it. We go to stat, enter. Let's clear all the lists. Second plus 4, enter. And this one, we just have 85. Oops, nope, not in that one. 85, 99, and 16. And then here, I just go ahead and do my 200 times 18 out of 38. I just let it do it for me right there. 94.737. And then I'll just do it again so it does the whole thing, even though I know it's the same number. 18 out of 38. And last one, 200 times 2 out of 38. And those are our expected. Now, in the past, I've showed you how to do L3, L1 minus L2 squared over L2, but I am going to do stat tests, chi-squared GOF test, because this is the type we decided. Now, you do have to put the expected yourself, and the observed we already did, and you do have to enter your own DF. So it's categories minus 1, there's 2, and then calculate, and it will do all the rest for you, though. So that's where all those numbers came from. And the C and T, RB are the components of the chi-squared test. The observed minus expected squared over expected for each one. So, Yeah, we can fill those in later too, the rest of the expected. All right, now hopefully that made some sense. And if not, just try it again and watch the AP Daily videos. I say one my table, GOF. That way it's all highlighted there for you to see. Okay, thank you so much for your participation. Have a great day. See you next time.